We went over because people weren't realizing it's 10 past 5.
Don't worry about it. I've timed it. It's like 10:30. It'll be really close.
Okay.
Don't worry about it.
How to influence enemies with win threats.
Thank you.
Looks like we're here. Okay, let's get going then so we can stay a little bit close to time. And we will start this session with Ian Roederer on the astrophysical art processes. Take it away.
Thank you. George, it is an honor to be back here with you again to celebrate another milestone birthday. You have this infectious curiosity about the world, I think. And Andy, Chris, do I get any back up here?
You get a compliment.
This doesn't come out of my time budget, does it?
This was Ian's method of showing something between pity and contempt for the UC Berkeley football team after Texas defeated them in a game at the time of his final exam for his PhD. He gave me this on the way back from a restaurant.
Okay, Ian, you get 20 more minutes.
Excellent. Keep talking, George. I'm just very happy to be back here with you again to share in this curiosity with you. And I'd like to actually share today some work that was inspired in some sense by the Objective Prism survey or the HK survey for metal poor stars. And of course, George and help Chris. I'm advancing the next talk because we switched things. Yep. Okay. Okay.
Minus
HK
19.
survey. Of course, George and Czech started this, and Tim did a lot of work on this as well. Many new classes of metal poor stars were discovered as part of the follow-up to this survey, including one class that is especially important to me. My favorite is the class of R process enhanced metal poor stars, and the inaugural member of this class, CS 22892-052, shown here. This class of stars now has many more members, but George and Andy and Chris and Leonard Searle were actually the first to publish on the remarkable spectrum of this star. And what's remarkable about that spectrum is the strong enhancement in the lines of these heavy R process elements. And the implication of that, which they helped to develop over the next few years along with John Cowan, the idea there is that the R process pattern in this metal poor old star is remarkably similar to the R process pattern that we find in the sun. And the implication of that is that there is something quite reproducible about the R process from one event to another to give you more or less the same pattern. And over the last 28 years since that discovery, a few hundred more of these stars have been found. A few of us even formed a small collaboration to work on this. We actually prefer the Collective Descriptor Alliance, which we found is really effective in helping us to evade funding opportunities. But we're now moving forward, working on finding many more of these stars and characterizing them to solve the big questions related to the R process. The R process is, of course, one of the fundamental ways that stars produce heavy elements. And it's a hot topic in many fields of astrophysics today, including multi-messenger astrophysics, because of its close connection with the kilonovae that are associated with merging pairs of neutron stars that can be detected in gravitational waves, as well as galactic astrophysics, for example, for their use as a chemical tag, for nuclear astrophysics as a way to explore the origin of elements all across the periodic table. Now, George and colleagues, of course, did not discover the R process, but I think the work that you all have done really helped to move it into the modern world of observational and stellar astronomy. So the question that I would like to pose today is this: which elements were produced by the R process and in what amounts? Our answer to this question for decades has been the solar R process abundance residual pattern, shown here. It is not measured, it is not self-evident, and it was not handed down from on high. Now, it has been incredibly useful to further our understanding of the R process, but it relies on a series of assumptions. It's what's left over, the residuals, after you subtract off the contributions from the S process and the P process. So the goal of our work has been to develop an alternative to the solar R process abundance residual pattern. And we have done this by finding another star that has the ability to detect many, many elements. So in this case, 42 R process elements in a star likely formed from the remnants of a single R process event that occurred in the early universe. And I would like to propose that this R process pattern should be adopted as a new, or at least an alternative, template to the solar R process residual pattern. So if you have your favorite model for kilonova nucleosynthesis or a rare kind of supernova that might host the R process, this is a pattern that one should aim to reproduce. So here's our main result. This figure shows the R process abundance pattern in this one star, HD 222925. And the figure shows log of the abundance, which you can just think of as another way of saying the number density, as a function of atomic number. The black dots mark the detections of these 42 R process elements. The red line marks that solar R process residual pattern if you just scale it downwards slightly to match the europium abundance in the star. And then the bottom panel there simply shows the differences between the stellar and the solar patterns. So let's quickly take a look at some of the more interesting features of this pattern. First, notice that for the heavier R process elements, there is remarkable agreement between the stellar pattern and the solar R process residuals. And heavier in this context refers to elements 56 through 90, so barium and beyond. That includes the lanthanides. It includes the third R process peak. It includes what seems to be everyone's favorite element when it comes time to write the press releases, whether or not you actually detected that element, gold. It also includes thorium, which is radioactive and depleted at a level that would be expected based on the old age of the star. Next, notice that for the lighter R process elements, the agreement is not quite so good, but the differences do not appear to be random. So the deviations show these gradual up and down trends with atomic number, and the stellar pattern actually matches pretty well with stars, other R process enhanced stars that have been observed previously, but where just more limited selections of elements were detected. We also detected elements at the first and the second R process peak. So selenium, tellurium, I swear all these elements are real. We detail all of this in our paper, and there's a lot to unpack here. The upside of the work is that we have now a reasonably complete R process template derived from a star enriched by probably just one R process event from the early universe. And the elements that have been detected are shown in colors here on the periodic table. In addition to the R process elements, we actually detected a total of 65 elements in this star. And to the best of my knowledge, HD 222925 now has the best known chemical inventory of any object beyond the solar system. And to put that in context for you, the star CS22892-052, the inaugural member of this class of stars. Eventually, 53 elements were detected in that star. And yet it took more than 2 decades and a star that was 4 magnitudes brighter to move in any reasonable way beyond that standard capability. So I think the legacy of CS22892-052 and stars like it discovered in the HK survey is very much secure in this field. So why did our study work? And can we do this for other stars? In short, it worked because we had access to high quality UV spectra from the Hubble Space Telescope. Many of these R process elements, the ones that are shown in blue, only present transitions for analysis in the UV part of the spectrum. And then when you combine that with a high quality optical spectrum, in this case collected with Mike at Magellan, that gives you the vast majority of the elements on the periodic table. And here are a few examples of absorption lines of our process elements in that UV spectrum. The other reason that our study worked is because HD 222925 is the UV brightest R process enhanced star that is known. So these spectra were collected over the course of 47 orbits with the Hubble Space Telescope. And having said that, we are still looking for other bright R process enhanced stars, but I think there's a very reasonable possibility that this star is going to be the only one from this class that gets observed in such exquisite detail until the launch of the next large UV optical infrared space telescope. And that will not happen until at least the 2040s. Now, a telescope like that, a mission like that, I think could collect spectra of this quality for a star like CS22892-052, which is much fainter. And if that happens, I look forward to welcoming all of you back here to celebrate George's 110th birthday. So thank you for your attention, and George, happy birthday.
Questions for Ian? Like,
Yeah, actually, I've thought of proposing a balloon-borne Shell spectrum that would bridge the gap, because I doubt that blue wire or whatever will have a high resolution Shell spectrum map on board.
Yeah, the question for Mike Rich is, have we thought about proposing a balloon-borne shell to do the UV spectroscopy? Not to the point of gaming it out, but we've had the idea, and some of the challenges that, at least that as I understand them, are you're limited to a relatively small, modest payload, and so you need something that can at least compete with HST, I think. So you need a decent aperture, even if you account for 30 years of detector technology and optics improvements. That might still be a challenge. Another one that I see is the pointing accuracy.
Now,
Because-
I think that there's a project called Firebolt.
Yeah.
The only problem may be, though, that you have to get very high in the stratosphere to get a decent UV. I think there will be anyway, we should talk, because it may be that certainly I know that Shimonovich and the UV group, Martin, with Fireball, they are doing a multi-object spectroscopic investigation.
Okay.
In the UV with a balloon, and it's a huge payload, and it's a very precision point.
All right, to sum that up for the folks online, we should talk offline.
Yeah.
Yep.
Anyway, sorry.
Yep.
any other questions here or online? Do we have anybody online?
Don't see any raised hands.
I'll just comment, many years ago, I was on a panel that chose the ultraviolet spectrograph. And I remember there was a reaction from NASA. They were very surprised that we went that way, but there were some of us on the committee who felt this was a unique capability of HST. So it's really nice to see this and many other results.
Thank you, Wendy.
If there's no other questions, let's move on. Oh, yeah, Mike, Tim.
Just comment. Just because we were sort of sitting in the same room when the idea came up, I should underscore that this RPA, the All Process Alliance, was centered around the initial observations with the DuPont 2.5. That's how we got started. Hanson was a postdoc here. And interested in such a project. So that formed the nucleus of what has become a relatively large group of similar people. But it started right here.
The comment from Tim Beers was that the origin of the RPA in some ways started here with Therese Hansen as a postdoc at Carnegie and wanting to do some follow-up on this with the DuPont. And in many ways that has led circuitously to where we are today with this. Yeah.
Okay, we'll move on then to Yutaka